Good day, guys. All right, so in this video, I want to talk about 8.2 equilibrium of uniform rigid body. All right, so before we can do that, we have to look at the term that is analogous to force in linear, but in this case, we want to talk about rotational dynamics or kinematics. All right, so let's look at the term in question, which is going to be torque. All right. So torque is this rotational kind of force. It stems from linear from force, but this particular force it allows or it causes the body, whatever body that may be, to rotate. Okay, so if you think about it, if you hold something at the edge of a table like a ruler, right? You hold a ruler at the edge of a table, and then you press down on one end that is not supported by table, you will see that the ruler bends, right? But if it's a rigid body, it will not bend, rather it will sort of rotate using the table as a fulcrum. Okay, so let's define torque. All right, let's define torque. Well, mathematically, what you do, you define it by you denote it by tau, and it's going to be the cross product between the r, which is the distance from that point of rotation, right, and force, the force that is causing it to rotate. Okay, so well, we've seen this product before, which is a cross product in chapter 1 when we talk about maths, right? Um, so obviously we can expand it so that we can only talk about their magnitude, right? And talk about the product of the magnitude r and f. Then we take the sign between them and the angle, right? And it's going to be normal to both r and f. Okay. All right, so how do we go about this visually, however, right? So let's draw the radius in one direction, a vector, not radius, sorry, the displacement, right? The distance, the displacement from the point of rotation, and then we have F in a different direction. Then let's put angles between them. Well, where does the torque go? Well, the torque is going to be normal to both R and F, right? It's going to be normal to both R and F. And the direction, rather than saying left or right, up and down, positive X or positive Y, we say that it's going to be clockwise or anti-clockwise, right? Or upwards or downwards. By the end of the day, is that it has to be normal to both F and R. Okay? Alright. So another name for torque is actually a moment of force, or turning effect, or rotational force. It varies between studies, it varies between fields of physics, but generally torque refers to this cross product between R and F. Okay? Alright. So the unit here, what we have, the unit here is Newton meter. Meter coming from the distance or displacement, and Newton is from the force. All right, so let's do a very simple sample problem, right? Involving a beam and a fulcrum. All right, let's see. A 3-meter beam of negligible weight, so we ignore the weight of the beam, is balancing in equilibrium. So in equilibrium, that means the summation of tau is going to be 0. Okay, with a fulcrum placed 1 meter from its left end. Yeah. So we have a fulcrum system, and then 1 meter from its left end. If a force of 50 Newton is applied on its right end, okay, which is 2 meters, how much force would need to be applied to the left end? So 50 Newton on the right end, how much force do I need on the left end? Well, if we think about it, if we split this to half, right, and we talk about this tau being towards the anti-clockwise, that's going to be R cross product with F, crosses with F, and the angle between them is 90, so sine 90 is just 1. It's just going to be the magnitude of r multiplied with the magnitude of f, where the magnitude of r is just 1. Okay, whereas on the right hand side we have tau clockwise, right? If you push it down, it's going to go like this, whereas this one, it goes like that. Again, the angle between them is 90, so what you have again is r multiplied by the magnitude of f. However, here we have 2 meters and here we have 50 Newton. Okay, because it says that in this question it is in equilibrium, where the summation has to be 0, right? We know, so the summation has to be 0, then we know the tau that contributes to anti-clockwise plus the tau in the direction of the clockwise, which is going to be negative, the opposite direction, is going to be 0. Sorry, this should be negative. Okay, one is in the opposite direction of the other, so it should be negative. And this should be 0. So then what we have is tau AC, anti-clockwise, must be the same as tau C. Okay, now remember, for the anti-clockwise, here we have 1 meter. And we are looking for the x value, the x Newton here. Okay, for the clockwise, what we have is 2 meters, and then the force is 50 Newton. Okay, so 50 Newton. So for the right hand side, what we have is 100 Newton meters, and on the left hand side we have 1 times x Newton meter. Okay, so this x actually has the value of 100 Newton, because 100 Newton multiplied by 1 meter gives you 100 Newton meter. Okay, and this can be easily seen if you just bring this 1 meter to the right hand side. Alright, so then what we will have is actually x equals to 2 meters times 50 Newton over 1 meter. Alright, so the final solution is how much force. The amount of force that you need will be 100 Newton applied to the left end. Okay, so it's no different than talking about equilibrium of forces, Fx, Fy, and Fz. In here, we are talking about torque instead. Alright, okay, that is all for this video. I'll see you in the next video. Thank you very much.